Right now, somewhere in the world, someone just hit send. A photo from Tokyo is traveling at light speed. A video from São Paulo is splitting into millions of fragments, racing along invisible paths. A financial transaction from New York is weaving through networks spanning continents. In mere seconds, all of it arrives perfectly intact on the other side of the planet. We treat this as normal. But here's the truth. This is a technological miracle. Every single day, billions of messages, videos, songs, and transactions flow across the internet simultaneously. Yet they almost never get lost. No dedicated pathway exists for each person. All data shares one colossal system. So, how does your photo not end up on someone else's phone? How does a song avoid tangling with a video call? How does your bank transfer reach exactly the right account? The answer isn't luck, it's ingenious design. What's even more fascinating is that no central brain controls the internet. There's no master control center. Billions of devices coordinate with near-perfect precision without any central authority. To understand how, imagine following a single photo from your phone to someone across the world. That journey takes us through smartphone memory, submarine cables, routers, and data centers. But before that image leaves your phone, it undergoes DOT, complete transformation, most of us have never witnessed. Everything becomes numbers. Music is not music. Video is not video. Everything gets converted into a universal language consisting of just two states, on or off. From these two simple states, humanity built the entire internet, smartphones, and the modern digital world. Understand this, and everything else becomes clear. Computers think in electricity, power flowing or absent, on or off. No, in between. From this principle, engineers created the bit, the smallest unit of digital information. A bit holds two values, 0 or 1. Sounds simple, but its power is nearly unlimited. Imagine having only two building blocks. Individually basic. But combine enough, and you build entire cities. Bits work the same way. 8 bits form 1 byte, the basic unit computers use to store data. A single letter needs at least 1 byte. But photographs contain vastly more information. Each pixel is stored as numbers representing color. Millions of pixels create the image you see. A modern photo contains tens of millions of pixels. Music gets processed the same way. Sound waves convert into enormous number sequences. Video is essentially thousands of images stored as complex numerical data. Whether photo, song, or film, everything becomes sequences of zeros and ones. This is why every device on Earth can communicate, regardless of manufacturer. Breaking data into pieces. That photograph has become millions of bits, a massive chunk needing transport. Does the Internet send the entire block at once? Absolutely not. Instead, engineers created an incredibly clever idea. Break everything into countless tiny pieces. Imagine moving a mountain of cargo with one truck. One malfunction, everything stops. Internet engineers realized a smarter approach. They divide data into manageable pieces called packets. These dots are the basic shipping units of the modern Internet. A few megabyte photograph gets divided into thousands of individual packets. Think of a giant jigsaw puzzle. Instead of shipping the entire painting, you send each piece separately. This creates a huge advantage. Packets don't need the same route. If one path is congested, packets take a faster direction. The Internet becomes like a massive city with countless roads instead of one shipping lane. But if packets travel different routes, do they arrive simultaneously? Usually not. Some cross oceans. Others travel through multiple countries. Some arrive before packets sent earlier. This sounds dangerous. If fragments arrive scrambled, how reassembles the image correctly? The Internet uses another genius idea. Each packet carries identification information. Think of puzzle pieces arriving with sequence numbers from the factory. No matter their arrival order, they reassemble perfectly. But each packet needs something more important, an address. IP addresses. Finding the way. That address tells the Internet exactly where data must go among billions of connected devices. With billions connecting simultaneously, how does a single packet know where to go? Without this system, the Internet would be like a massive city dot where every house has no address. Delivering accurately would be nearly impossible. That's why the Internet created IP addresses, home addresses for devices in the digital world. When you send a photo, packets carry the sender's address and recipient's address. Like an envelope marked from and to, but packets are far more sophisticated. They carry additional information, helping the Internet control their journey. This extra information is called the header, like a passport for packets. Headers tell packets where they're coming from, where they're going, and what rules apply. Every time a packet passes through a network device, the header gets examined. Like traveling through international airports, with passport checks at each point, packets operate similarly. Every router reads the information before deciding the next step. Routers don't care if a packet contains photos, music, or video. They only care about the address. This simplicity lets the Internet handle enormous volumes at incredible speeds. Routers, the smart intersections. Packets need to know the fastest route to their destination. This is where routers show critical importance. Every second, routers worldwide make billions of decisions about packet directions. Those decisions guide your photo across oceans and continents. With billions connecting simultaneously, no human can direct each packet. That job goes to special machines called routers, the intelligent intersections of the Internet. When a packet reaches a router, the device reads the address and decides the next step. This happens in millionths of a second. Routers maintain special maps describing available pathways. These maps aren't fixed. The Internet changes every second. If a cable fails or overloads, packets instantly reroute in different directions. This remarkable resilience lets the Internet survive even when parts malfunction. During its journey, a packet passes through many routers. A photo from Vietnam to America might travel through dozens of waypoints. But here's the surprising part. Most doesn't travel through air. It travels under the ocean. Over 90% of international Internet traffic goes through massive submarine cables. Inside these cables, data flows as incredibly fast light pulses. Those tiny rays carry videos, calls, and data for billions daily. When packets disappear, no matter how smart routers are, one unavoidable problem remains. Sometimes packets vanish mid-journey. This packet loss happens for many reasons. Sometimes networks are overloaded. Too much data through a narrow point. When a router's memory fills up, some packets get discarded. Hardware failures or damaged cables make data disappear. Even undersea earthquakes interrupt international lines. If packets get lost, is your photo permanently damaged? Usually, no. The Internet shows one of the most intelligent mechanisms ever invented. When sending data, computers don't just transmit and forget. They constantly monitor each packet's journey. Once packets arrive, the receiving device sends confirmation. If no confirmation appears after a certain time, the computer suspects loss and simply resends that packet. This happens so fast, users never notice. Thanks to this ability, the Internet stays stable even in risky environments. But constantly resending creates a new problem: performance and speed issues. The system needs quick error detection, checksums, and protocols. Every second, quadrillions of bits rush across the Internet at near light speeds. Greater speeds mean greater mistake risks. One single bit changing from 0 to 1 can make content completely different. With photos, errors might be wrong pixel colors. With banking, consequences are far more serious. The Internet needs constant data verification. Before sending a packet, computers create a special mark dot called a checksum, like a fingerprint, from the packet's contents. When the packet reaches its destination, the receiving device recalculates the checksum using the same algorithm. If checksums match, the packet is intact. If not, it's corrupted. Two important protocols ensure data integrity: TCP and UDP. TCP works like a meticulous delivery manager. Each packet comes with error-checking information. TCP ensures packets arrive in correct order and completely. If packets are lost, TCP detects gaps and requests resending. TCP also controls transmission speed, preventing overload. But this carefulness has a cost. It slows data transmission. UDP gets chosen when speed matters most. UDP is faster and simpler, sending packets without waiting for confirmation. It doesn't verify errors or reorder sequences. This makes UDP perfect for applications needing instant responses, video calls, and online games. A few dropped frames sometimes beats waiting for complete resending. Video applications use their own algorithms, predicting and compensating for lost frames. Buffering, the waiting strategy. There's one more clever idea: the buffer. Buffers act like small data warehouses. When you press play on a video, the device preloads data before starting playback. If packets arrive late or get lost, the video continues normally briefly. Only when the buffer empties do you see that spinning circle. That frustrating circle actually rescues content from constant interruptions. The Internet constantly balances speed, accuracy, and user experience. How it all works together. Finally, we have puzzle pieces to solve the biggest Internet mystery. Why doesn't data get mixed up traveling across the Internet? It's not magic, but countless clever engineering ideas. A photo transmits as millions of simple data bits. Those bits break into thousands of packets for transport across the global network. Each packet carries its own address, like a marked letter. Routers read addresses and find the best path among millions of options. Packets might travel through many countries, different networks, and even under oceans. If packets get lost, the system detects and resends them. If data gets corrupted, checking mechanisms catch it immediately. TCP monitors every packet, assigns sequence numbers, and reassembles them into complete data. UDP helps real-time applications run smoothly by prioritizing speed. All these mechanisms coordinate constantly, billions of times every second, without any central brain. This makes the Internet one of humanity's most complex systems. Every day, trillions of packets get sent, most reaching exactly the right destination, despite crossing enormous distances. With just one finger tap, a photo begins a journey spanning thousands of kilometers. A few seconds later, those data fragments reassembled perfectly on the opposite side of the world. From a user's perspective, everything seems instant. But behind that simplicity lies enormous technological achievement. Perhaps the most amazing thing isn't the Internet's speed, it's the stunning accuracy. A world where billions share one system, yet data still finds its correct path. Next time you send a photo, remember, behind that tap lies one of humanity's greatest achievements.